Okay, so we're in the home stretch. Two more class days, today's class, Thursday's class, and then we're into finals. So the plan for today, oh, we did finish this up last time. So the plan for today is to discuss 8.4, adding and subtracting rational expressions with unlike denominators. So we talked about adding and subtracting with like denominators last time. The plan for Thursday's class is to wrap up, I guess, the fairly small section. We might not even take the whole class. 8.5, simplifying complex rational expressions. So when we have kind of like the quotient of two rational expressions, or like a rational expression consisting of rational expressions. And then the week of Friday the 2nd to Friday the 9th is our final exam week. So the proper final exam week is really next Tuesday through that basically Friday or Saturday for most classes. But I'm opening up the final exam a few days early, so that way you have the weekend. If you want to use the weekend, of course, you can certainly feel free to take it Tuesday, Wednesday, Thursday, Friday during final exam week proper if you want to. Couple of notes, the sample final is up now on WebAssign. I don't know why it is that my allergies always just uh, start bugging me as soon as I start talking in the morning and then seem to level out after that. But the sample final is available now, so you can check that out for have an idea of how long the final will be, the types of problems, and so on, and to assess your preparation for it. The final is to be taken on WebAssign. It'll open up this coming Friday the 2nd at 9 a.m. It's the same setup as the unit exam, so it'll pretty much just feel like another unit exam. And just a reminder, don't wait until the last minute of the last day to complete the exam. There are no due date extensions on exams. So I would recommend you plan to complete it on or before Wednesday night. That way, if anything does go wrong, you've got kind of 2 full days, Thursday and Friday, to reach out to me to work out a solution to come up with a remedy for that. Okay, the quote of the day today is kind of an idea more than a quote, but don't underestimate the impact of survivor bias. So what is survivor bias? We talk about this sometimes in our statistics course. And that's where if we look around us right now, at a lot of different in a lot of different facets, but if we look around us right now, what we observe today are the quote survivors of whatever process, right? So one kind of classic example of survivor bias is in World War II, there was this statistician, Abraham Wald, who was contracted with the Royal Air Force. They wanted to put more armor on their planes, but of course you can't turn a plane into a tank. You can't just put a bunch of armor everywhere because then it can't take off and it can't maneuver and so on. So they wanted to place the armor strategically, and they asked him, where should we place the armor? What's the best place to put a little bit of armor to increase the efficacy of the planes, to reduce their chance of getting shot down, but also not to burden them too much so they can still take off. They don't use too much gas. They can still maneuver. So the so what he did is he would sit on the side of the runway and look at the planes coming back from planes go out, get in a dogfight, come back. And he wrote down where the bullet holes were on the planes that came back. And maybe somewhat surprisingly, where he recommended to put the armor is where he saw no bullet holes, because presumably the ones that came back were the survivors, and the ones that got hit in, say, the engine or the cockpit, where he saw no bullet holes in the ones that came back, those ones presumably were the ones that went down. So that's an example of survivor bias. You can Google survivor bias, and there are lots of different classic examples. But I think it's important to remember that the end result of anything is dependent on some uncontrollable systematic effects, that the, maybe person in question, you look at a person and say, oh, they have a great career, I would like to follow their career path. Well, there are some systematic effects that they had no control over that just kind of happened to them. There are controllable systematic effects, things like, what do you choose to go to school for? Or, what career choices do you make? How do you choose to, what places do you choose to interview with? Things like that. And then, of course, there's always a component of chance or luck as well. Um, and as Charlie Munger would say, that these large outliers are likely a confluence of many tendencies. It's likely that a lot of different things, controllable and uncontrollable, came together to produce a large outlier. So some examples are, in strength training, people will say, oh, well, Arnold Schwarzenegger trained this way. He described it very in much detail in a couple of older books. And well, I'm going to train that way because Arnold trained that way. Well, then they train that way for a month and their joints feel terrible. They feel beaten down. It's like, yeah, because you're not Arnold. Arnold had great genetics. He had, he was devoting his entire and the entirety of each day to working out and recovering and all of that. And, you might have kids or a job or going to school or whatever that's, tying up some of your time. So yeah, you're not Arnold. So following Arnold's workout program probably is not going to be successful for you. Maybe, 1 in 1,000 people can follow that program and do the amount of work that he did in a given day or week and actually be successful at that. Or another example is Robert Kiyosaki, the author of Rich Dad, Poor Dad, his financial strategy. So he describes his financial strategy. I forget if it's in Rich Dad, Poor Dad or his next book, the Cash Flow Quadrant. But basically what he describes is he went into real estate and he adopted the approach where he took out tons and tons and tons of loans and debt. So he had a bunch of real estate, but they were all like underwater in debt. Everything was in the red. And his argument was, well, having all of these creditors, like these banks and people constantly calling him and being like, you're behind on your payments, that would stress him out and it would drive him to find a way to make those payments. And eventually he got caught up with everything and came out way ahead, way on top. It's like, yeah, that's great. But how many people tried that and failed and ended up in bankruptcy? Dave Ramsey is kind of the other extreme, like take on no debt because he did a similar thing in real estate and ended up bankrupt, right? And it kind of completely changed his viewpoint. Or how many people do that and end up so stressed out that their mental health suffers or they can't sleep or right. And so you look at Robert Kiyosaki and you think, oh yeah, that's really cool. If I take his approach and it works out, yeah, if it works out, that's great. But how much of that is reliant on effects that aren't under your control? Probably quite a bit. So don't underestimate the impact of survivor bias. If you read these biographies of highly successful, highly influential people, take that as I think there's a saying something like, consider that inspiration, not aspiration. Don't say, okay, I'm going to do exactly what they did because I want to end up where they were. Say, wow, that's amazing. Somebody could do that. Let me try to make my life better in the way that's going to work for me. So I guess a bit of a long discussion there, but I think survivor bias is an important idea coming out of probability and statistics and so on. If you're interested in that course down the road, Math 165, I think it's a great course. And all right, that's about what I have to say about that. Okay, so moving on to 8.4, adding and subtracting rational expressions with unlike denominators. All right, so like we've done before, let's take a look at, in some sense, the simplest rational expressions, just numerical fractions. And if we start off with a fraction with like denominators, just to recall how this works, if we have two fractions with like denominators, if we're adding or subtracting, I've just chose addition for these three examples, but subtraction would work very similarly. Well, basically what we have is we have like a pizza that's sliced into 6 slices, and I have one of those for 1/6. And I have another pizza sliced into 6 slices. And for this one, I have 5 slices. So if I put these together in the same box or boxes, how many pizzas do I have? Well, I have 1 slice plus 5 slices. What are the size of the slices? Each of those slices is 1/6 of a pizza. So when I have the same denominator, when I have the common denominator already, I add the numerators, and importantly, I keep the same denominator. I don't like add the denominators. I don't get 6 plus 6 is 12. My slices don't magically turn into 1/12 of a pizza size. They're still 1/6 of a pizza. They're still the same size. But I just have more of them when I add together the 1 plus the 5 and put them together. This gives me 6/6. And then, of course, I simplify at the end. I want to write this in the simplest form possible. So I divide out the common factor of 6 and get 1. Okay, so probably no surprises there. What if I have something like 1/3 plus 1/4? Well, here I've got one pizza from maybe Pizzeria A. They slice their pizza into thirds. Strangest pizzeria in the world. It would be quite difficult, I think, to cut a pizza into thirds, but that's how they do it. We have another pizzeria, Pizzeria B, that slices their pizzas into quarter size slices, and we have one of those pieces left. And we want to put those together in the same box and figure out what proportion of the whole pizza we have left over. Well, we can't just add them together. I can't say this is 2 slices because the slices are different sizes. We're, in a sense, comparing apples to oranges at this point. One slice is bigger than the other one. So I need to figure out a way to make the slice sizes the same. Basically, what I'm going to do is take each of these slices and chop them up into smaller slices. I'm going to make further slices or further cuts in these slices so that maybe instead of one slice at 1/3 size, maybe I could have 2 slices at 1/6 of a pizza size, or maybe 3 slices at 1/9 of a pizza size, or something like that. So how do I know how much to slice each of these pieces up? Well, the first thing I need to do is I need to find my lowest common denominator. So I write my prime factorization. 3 is just 3. 4 is 2 squared. So my lowest common denominator, this is in a sense, I like to make the analogy of like a Lego set. If I were to hand you a Lego set and your goal was to be able to build a 3 and also to be able to build a 4, not necessarily at the same time, not necessarily have a 3 sitting next to a 4, but to be able to build a 3, or if you disassemble the 3 to be able to build a 4, what Legos would I need to give you? Well, I need to give you 1 3. That's the prime number that's needed to build a 3. I mean, this is pushing it a bit, the analogy a bit far because these numbers are so small, but and then I would need to give you 2 blocks of size 2 because you also need to be able to build the 4. Or this is 12. Now, it turns out that in this case, your kind of 2 goals with the Legos are different enough that they don't share any common pieces. So I just need to give you all of the pieces to build the first one, plus additionally all the pieces to build the second one. But we'll see in the next example. Sometimes we can get away with a smaller Lego set and being able to build both of them if we repurpose some of the pieces. Okay, so my first thing is that I see that I want to make slices of size 1/12 of a pizza. I remember that just like up here, 6/6 equals 1. Well, that also means that 1 equals 6/6. And I know that if I multiply by 1 or if I multiply by a number over itself, I don't change the value. So I want to take 1/3 and I want to multiply it by a number over itself to get this denominator of 12. I see I have the 3 already. I need 2 more blocks of size 2, 2 2s or 4. So I need a 4 in the denominator to make it 4 times 3 is 12. And I need 1 in the numerator as well, so that net I'm multiplying by 1. I'm not changing the value. I'm not changing the amount of pizza I have over here. But what I'm doing is I'm slicing it 4 more ways. Well, I'm slicing it 3 times and making 4 pieces where there were previously 1. I do the same thing with 1/4. What do I need to multiply 1/4 by to get a denominator of 12? I need to multiply the 4 by 3. And then because I want to maintain the same size, the same amount of pizza, I multiply by the same number in the numerator. So I'm slicing this 1 piece, cutting it 2 more times, making it into 3 pieces where it was previously 1. Now in this first product here, 1/3 times 4/4, now I multiply together and I get 4/12. In other words, I'm just choosing to represent 1/3 of a pizza as 4/12 of a pizza. I've kind of like unsimplified in a very specific manner. And then for my second, I have 3/12. And the nice thing is that now that I've sliced my 1/3 piece of pizza into 4 slices and my 1/4 piece of pizza into 3 slices, now all of my smaller slices are all the same size. They're all 1/12 of a pizza. Now I can just put them in the same box and count them up. Now I can just add 4 plus 3 is 7/12. 7 is prime, no common factors. That's our answer. I'm going through this in a good bit of detail because I know that some people don't like fractions so much, but also I want us to really focus on what's going on behind the scenes and the process that we're going through so that we can apply a similar process when we get to harder problems with the rational expressions. So focus on the underlying mechanics here rather than the details of the numbers. Okay, now I have a similar type of situation with 1/6 plus 3/10. My 2 denominators are different. I have 1 slice of pizza that's from a pizza that's cut into 6 slices of size 1/6. And I have 3 slices from pizza that's cut into 10 slices. How do I make these slices the same size? And then how do I add them together? I do a similar thing over here. 6 is 2 times 3. So when I hand you a bag of Legos and you say I want to be able to build a 6, it's got to be at least a 2 and a 3 block in there. 10 is made up of 2 times 5. That's its prime factorization. So actually, I could hand you a bag of Legos that has 1, 2, 1, 3, and 1, 5. You could use the 2 and the 3 to build a 6. Then you could take them apart and use the 2 and the 5. You could reuse the 2 along with the 5 in the bag to make a 10. So I actually don't have to hand you 2 2s, a 3, and a 5, because the goal is not necessarily to be able to make a 6 and a 10 at the same time. It's just to be able to make a 6 and then disassemble it and take the same bag of Legos and be able to make a 10 out of it. So 2 times 3 times 5, well, that's 6 times 5 or 30. Note that that's less than the product. 6 times 10 would be 60, right? I'd be looking for a common denominator of 60 if I was looking to be able to like build a 6 and a 10 at the same time. But that's not what the common denominator necessarily has to do. So we want to find the lowest common denominator. We could use a common denominator of 60 and that wouldn't be the end of the world, but it would make a lot more work for us because we'd be dealing with bigger numbers and then having a lot more to simplify at the end. So we might as well use the lowest common denominator, which is 30 here. Now I take 1/6. I see that my 6 uses the kind of 2 and 3 block. What do we have to append onto the 6 to make our whole common denominator? We need to pick up a 5, right? We've used the 2 and the 3. We also need a 5. So I want to multiply by 5/5. This gives me a denominator of 6 times 5 is 30. That's exactly what I want. And then similarly, 3/10. 10 uses the 2 and the 5. What do I need to append onto that 2 and 5 to kind of make this whole set of building blocks? I need to pick up a 3. So the denominator 10 times 3 gives me 30, and of course I multiply by 3/3 so that I don't change the value. Now I take this first product, I multiply across, I get 5/30. So just writing 1/6 as 5/30, it's the same value, it's the same amount of pizza, but instead of thinking of one slice from a pizza that's sliced into 6 pieces, I'm thinking of 5 slices from a pizza that's sliced into 30 pieces. Then similarly with the second product, we get 9/30. Now my slices are all the same size between the two pizzas. I've sliced a bit more until everything is a bunch of slices of size 1/30 of a pizza. I have 5 of them from the first pizza and 9 of them from the second pizza. I just add those together and get 14/30. And at this point, I would like to simplify. I do notice that I have at least a factor of 2 in the top and the bottom, so I can write this as 2 times 7 over 2 times 15 and divide out the 2's. And I think with 7/15, that's in simplest form. 7 is prime, 15 has no factor of 7, 3 times 5. So that's as simple as we can get it. Okay, so now let's move on to adding some rational expressions with unlike denominators. We'll start with denominators that are monomials, and then we'll progress to denominators that are polynomials, maybe binomials, maybe trinomials. Okay, so let's look at these two rational expressions here. I see 5 over 3xy cubed and 1 over 2x squared y. What's the first thing I did up here? Well, the first thing I did is I looked at a prime factorization. I looked at what are the building blocks, what's kind of the minimal set of building blocks I need to give somebody to be able to build all of the denominators. Let me try to do that here. I have one denominator that is 3xy cubed, another denominator that is 2x squared y. Trying to make that cube look a little nicer. There we go. Okay, so let's go piece by piece. I'll look at the number first in 3xy cubed. The number 3, does it factor into anything? What's its prime factorization? Well, it's pretty simple. It's just 3. So I kind of need a 3 building block in my set of blocks to be able to build a 3xy cubed. I'm going to give a little bit of space for the number down below. I need some x's as well. To build the first denominator, 3xy cubed, I only really need 1x. I just need 1x building block. And I need some y's as well. And I need 3 of those. So to build the first denominator 3xy cubed, I need a 3 building block, an x building block, and 3 y building blocks. For the second one, I need a 2 building block. 2's prime factorization is just 2. I need some x building blocks. I actually need 2 of them to build the second one. Oh, Java is trying to do something on my computer and popping random stuff up. All right, 2x squared. So we need 2 building blocks for x. And we need some y building blocks as well for the second denominator, but we only need 1 of those. So I'm going to come down each of these columns. I need a 3 building block. I need a 2 building block. For the x building blocks, I need to have 2 of them so that I can build either of the denominators. And for the y building blocks, I need to have 3. So I'm taking the highest power from each column. Or this is 6 x squared y cubed. This is my LCD. Now let me take a look at my first denominator, 5 over 3xy cubed. And I can ask myself, what do I need to multiply 3xy cubed by to make a 6x squared y cubed? Well, the 3 needs to multiply by the 2. The x needs to multiply by another x to make the x squared, and the y cubed is already taken care of. So I think I need a 2x here. That'll give me 3 times 2 is 6. X times x is x squared, y cubed. That is exactly my LCD that I'm looking for. Now I multiply by 2x on the bottom, I better multiply by 2x on the top as well. I'll do a similar process with the second rational expression, 1 over 2x squared y. What does 2 need to multiply by to make 6? It needs to multiply by 3, right? We're missing the 3. What does x squared need to multiply by to make x squared? Well, that's good to go. What does y need to multiply by to make y cubed? That needs to be y squared. So if I multiply 2x squared y by 3y squared, I should get 6x squared y cubed, the common denominator I'm looking for. And then, of course, I multiply by the same thing in the numerator as well, so that really I'm just multiplying by 1 and not changing the value. That's equal. And now I take each of my, right, what was the next step? I take each of my products, I multiply them together, and write that answer. So in the numerator, I have 5 times 2x, that is 10x, over 6x squared y cubed. And to that, I'm going to add the second product. 1 times 3y squared is 3y squared, over 2 times 3 is 6, x squared y cubed. And I do see that indeed I have the same denominator now. I have pizzas that are now sliced into slices of size 6x squared y cubed. And how many of those slices do I have? I have 10x on one hand and 3y squared on the other hand. So we're speaking much more abstractly now. We're not slicing a pizza into 6 pieces, which is very easy to think about and visualize, but we're slicing it into the strange 6x squared y cubed slice size. But the mechanics still work the same. I add my numerators, which represent how many slices of pizza I have, 10x on one hand and 3y squared on the other hand, and I keep the same denominator. My slice size has not changed in this step. 6x squared y cubed. Now I look at my numerator, 10x plus 3y squared. Does anything, do I have any like terms that combine together? Does anything simplify there? Can I factor anything? No, I don't have a greatest common factor. My numbers 10 and 3 don't share a common factor. My variable components, the x and the y squared, don't share a common factor either. And 10x plus 3y squared, those are unlike terms. So this is really the best that I can do. Okay, let's take about maybe 7 minutes or so and work through these two. I think working through them on your own, I took quite a bit of time going through the details very carefully. I think working through them on your own will go a little bit faster, but we'll do maybe about 7, maybe 8 minutes. We'll see kind of how things proceed on these two exercises. So take a look at these two, work through them, and then we'll come back in 7 or 8 minutes and discuss the answers.
Let me do it. No, not real. Your groovy smoothie.
Somebody have a question? I think somebody is unmuted. Okay, it's right around 8 minutes now. So let's take a look at these two. So for the first one, if we look at our denominators 5x y to the fourth and 3x cubed y squared, we come over to the side and we can write out their prime factorizations, which are pretty simple. We just basically end up with 5 times x times y to the fourth and 3 times x cubed times y squared. So I need one building block of size 5, 3 building block. I need 3 x building blocks and 4 y building blocks. Or that makes 15x cubed and y to the fourth for our lowest common denominator. So we look at our first fraction, 4 over 5xy to the fourth. And 5xy to the fourth, up here, what does it need to pick up to become the same as the lowest common denominator? Well, it needs a factor of 3. And it needs 2 factors of x so that it has enough x building blocks. It already has 4 y's, and that's all that it needs. So we need to multiply 5xy to the fourth by 3x squared to make 15x cubed y to the fourth. And if I multiply that on the bottom, I better also multiply it on the top. Similarly, my second fraction, I need to multiply by 5y squared over 5y squared to make the denominator 15x cubed y to the fourth. Now I take my first product here, multiply those together. 4 times 3 is 12, x squared in the top, and then I get 15x cubed y to the fourth in the bottom. For my second product, 2 times 5y squared is 10y squared in the top, and the same 15 x cubed y to the fourth in the bottom. I add those together by adding the numerators, 12x squared plus 10y squared, divided by the same denominator. Remember, the denominator is basically the slice size. That's not changing when we just add these together. 15x cubed y to the fourth. And I guess we can factor a common factor of 2 out of the numerator, but that doesn't divide with anything in the denominator. There are no factors of 2 in the denominator, so this is really our simplest form. You could probably write it with the 2 factored out or without. I would argue it's the simplest form in either case, but I think it's a good step to factor out the 2, just because once we get everything factored, we can see very clearly whether there are common factors to divide out. There don't happen to be in this case, but in another case, there could be. Okay, in the second exercise, we have 7 over 48y squared minus 1 over 30x squared y. So my numbers here are a little bit hard to get a prime factorization for. They're a little more challenging. But I noticed that 48, I can write as, say, 6 times 8. And 6 is 2 times 3, and 8 is 2 cubed. So 48 is going to be 2 to the fourth times 3. So 48y squared's prime factorization is 2 to the fourth times 3 times y squared. And let me shimmy this y squared over a little bit so that it is more above the other y. There we go. If I look at the number 30, I see that 30 is 6 times 5, for instance, and 6 is 2 times 3. So 30 can be written as 2 times 3 times 5. And then x squared y, I have one factor of y, and then 2 factors of x. So I see that I need 2 building blocks. How many do I need? I need 4 of them to be able to build either one of these denominators. I need 1 factor of 3. I need 1 factor of 5, 2 factors of y, and 2 factors of x. Or 2 to the fourth times 3 times 5, I see that one of these 2's can combine with a 5 and make it 10, leaving me with 2 cubed, which is 8 times 3. Or 8 times 3 is 24, times 10 is 240. So my LCD is 240 x squared y squared. So that's what I'm going for in my denominators. Now my first fraction over here, 7 over 48y squared. The 48y squared has 4 factors of 2 and a factor of 3 already. What do I need to pick up? I need to pick up a factor of 5 to make the numbers work out right. And then what about the variables? I have a y squared, but I need an x squared. So I need to multiply this first fraction by 5x squared in the denominator, and then of course in the numerator as well, so I don't change the value. And I do a similar thing over here, 1 over 30x squared y. The 30 has one factor of 2, so I need to pick up 3 factors of 2. 2 cubed is 8. It has one factor of 3 and one of 5, and that looks just right. So I just need a numerical factor of 8 to multiply on. What about the variables? I have 2 factors of x already, and that's what I need, so I'm good there. But I only have one factor of y, and I need 2. I need to pick up an extra factor of y. So I need to multiply by 8y on the bottom, and then also, of course, on the top. Now multiplying my first product together across the top gives me 7 times 5 is 35x squared over the common denominator. I did this in kind of one line here, minus, for my second product, I have 1 times 8y is just 8y over my common denominator. So I end up with 35x squared minus 8y, all divided by 240x squared y squared. My terms in the numerator, they're unlike terms. They can't combine together. They have different variables and different powers. Can anything factor out? This isn't like a difference of two squares or anything like that. There's no greatest common factor that can come out. One has only x's, one has only y's. So there are no variable common factors. And one, the 35 is 7 times 5, and the 8 is 2 cubed. No common factors between the numbers either. So this is the simplest I can make it. Okay, any questions on these? All right, let's take a look then at a slightly more complicated situation. So here I have two rational expressions being added together. They have unlike denominators, but the denominators aren't just monomials, they're actually binomials. 3 over x plus 1 plus 5 over x minus 3. Now let me think. Let me go through the same process. I have x plus 1 and x minus 3. What are like what's like the equivalent of the prime factorization for these? I might be tempted to do something like, 1 and x and then like 3 and x, but that's not multiplied, right? So we don't want to do that. Well, actually, x plus 1 is prime. If I told you, factor x plus 1, you would probably say, well, it's prime. I can't factor it. So x plus 1 is just like its own building block. It's like a number 2 or something like that. You can't factor it. It just is what it is. It's one of the fundamental building blocks. And same with x minus 3. That's also prime. It's like, the number 5 or something. It's a fundamental building block. So if I want to give you a bag of Legos, so to speak, a bag of building blocks, and you be able to build an x plus 1, there needs to be an x plus 1 in there. And you just pull it out and sit on the table, and there's your x plus 1. There also needs to be an x minus 3 in the bag. So what's my LCD? I need one factor of x plus 1 and one factor of x minus 3. That's my LCD. Right? Hopefully we see that this is the same pattern as above. The important thing that we're looking for here is that the kind of prevailing operation that we're considering is multiplication. So an x plus 1, that's kind of its own thing. It's not multiplied onto anything else. Same with the x minus 3, it's like its own thing, and it's not multiplied onto anything else. So now I come down at my first fraction is 3 over x plus 1. I have this denominator. Let me put it in parentheses. That certainly doesn't hurt anything. I want to multiply that x plus 1 by something to make the LCD. What do I need? What building block or building blocks is not contained in the x plus 1? Well, the x minus 3. So now I have x plus 1 times x minus 3. I have a denominator that's going to turn out to be my LCD. But again, I don't want to change the value of the thing, so I better multiply by the same thing in the numerator. Just like before, this nets out to 1. I'm just multiplying by 1 in a creative way. Essentially, what I'm doing is kind of unsimplifying in a very specific manner. And then I have plus 5 over x minus 3. I'll choose to put this x minus 3 in parentheses. And then I want to multiply by something so that my denominator turns out to be the LCD, the lowest common denominator. Well, I have an x minus 3 already. I need to pick up an x plus 1. So I'll multiply by x plus 1. This should give me a denominator that's the LCD, but again, I have x plus 1 that I multiply by in the bottom. I better multiply by it on the top as well. Okay, now let's take my first product here. Multiply the numerators. Let's start with 3 times x minus 3. And then the denominators, x plus 1 times x minus 3. And then my second product, 5 times x plus 1. I'm being careful with my parentheses here. So I don't have like 5x plus 1. I have 5 times parentheses x plus 1. Just be careful with that. We might need a distributive property or something to come into play. Then I have x minus 3 times x plus 1, but I know multiplication is commutative, so I can just choose to write that as x plus 1 times x minus 3 to make it look like the previous one. Well, now I have two fractions with the same denominator. I add the numerators. And put it over the common denominator. Remember, my denominator is just telling me the slice size. When I accumulate more slices or take slices away, that doesn't change the slice size. So just same denominator. Okay, I mean, I've made progress, but I need to simplify now. So what might I want to do? Well, my denominator is already basically factored, right? It's already split into like its prime building block components. It's something like a basic building block times a basic building block. But my numerator isn't like that. My numerator has stuff connected with a plus. So I think what I want to do in my numerator is I want to rework my numerator so that it's something times something. Well, that means distributing both of these, combining like terms, and then factoring. So I get 3x minus 9 plus 5x plus 5 over my denominator of x plus 1 times x minus 3. Now I combine like terms, 3x and 5x, those are like terms. So I do 3x plus 5x is 8x. Minus 9 plus 5 gives me minus 4. And my denominator stays the same, x plus 1, x minus 3. My numerator, I can pull out a 4. And I'm left with 2x minus 1. And my denominator, x plus 1 times x minus 3. Does anything divide out? No, I don't have any common factors here. So this is the best that I can do. This or perhaps this. But it is important that I go to this end and just double check. There's nothing that can divide out. Let's look at something like this one. 3 over x squared plus 3x minus 18 plus 4x over x squared plus 8x plus 12. So let's come over to the side. So let's start with x squared plus 3x minus 18. I want to get something like a prime factorization for this, or really I just want to factor x squared plus 3x minus 18. So I'm looking for, geez, my threes are not looking too good today. I'm looking for two numbers that multiply to negative 18 and then add to 3. I think that's going to be, well, it's going to be something like 6 times 3, right? One being plus, one being minus. I think that's going to be a plus 6 and a negative 3. If I multiply those, 6 times 3 is 18 with the negative, that looks right. And if I add them, 6 minus 3 is positive 3. So this factors into x plus 6 times x minus 3. These are the building blocks that I need. I need an x plus 6 and I need an x minus 3 to make a x squared minus, or x squared plus 3x minus 18. The same way that way back here, I needed like a 2 and I needed a 3 building block to combine together to make a 6. Same idea down here, just with some variables, and it's a bit more abstract. What's my other denominator? X squared plus 8x plus 12. I know that 6 times 2 is 12, and positive 6 plus positive 2 is positive 8. And so I think this is going to be x plus 6. I have that same building block I can share between the two of them, but then I have an x plus 2 that's a new building block that I need. What's my LCD? I need one of the x plus 6 building blocks. I could use it on one hand to make the blue quadratic, or I could disassemble that and use that x plus 6 in a different context to make the green quadratic. I need an x minus 3 building block, and I need an x plus 2 building block. So this is like getting our prime factorizations for numbers, but we're just doing it for these expressions with variables. But this is my LCD. Note that my LCD isn't just the product of the denominators. I was able to reuse the x plus 6, so I saved myself the hassle of having an extra x plus 6 building block floating around that would just make things more complicated in the intermediate steps and then be more difficult to simplify at the end. Okay, so let me jump all the way down here so I have a little bit more horizontal room. Let me take a look at my first fraction. I could write it as 3 over x squared plus 3x minus 18, but we see that it's a little nicer to write it as 3 over x plus 6, x minus 3. I want my denominator to have one x plus 6, one x minus 3. We've got those, but also an x plus 2. So I need to multiply by x plus 2 in the denominator. And if I do that, I better multiply by it in the numerator as well. Now for my second fraction, and we've got 4x over, well, I could write it as x squared plus 8x plus 12 if I wanted to. That wouldn't be wrong, but it's much more helpful to write it as x plus 6 times x plus 2. Now I see I've got one of these and one of these building blocks accounted for, but I need an x minus 3 building block. So I multiply by x minus 3 in the denominator, and then of course, to not change the value, I do that in the numerator as well. This is, of course, equal to the previous thing. And now I continue on with my process. I multiply this product together. So I have 3 times x plus 2 over x plus 6, x minus 3, x plus 2. Then I see I'm also going to have plus 4x times x minus 3 over that same denominator. I'm going to cut out a step here and just do plus 4x times x minus 3, like that. If you wrote an extra step in there, no big deal. But we're starting to see this pattern. We always write these these two rational expressions, but they have the same denominator at this point by construction, and then we just combine them together. That's a pretty simple step to do, so I just combine them together from the outset. Now again, I don't see immediately a common factor that can factor out of the numerator. The denominator is already factored, so I don't want to mess with it. I also don't want to do something like this. That's not valid, right? I need to, if I'm going to divide out common factors from numerator and denominator, that I need to have a factor times the rest of the numerator and a factor times the whole rest of the denominator to do that. So where do I go from here? Well, I multiply out my top. I combine like terms, I factor, and then I look for common factors. And I'm going to pop over here to some scratch work to simplify this numerator. So I end up with 3x plus 3 times 2 is 6, plus 4x squared, and then minus 12. Whoops, minus 12x. So I get 4x squared minus 12x plus 3x minus 9x, and then plus 6. Do I have any common factor that could come out? Not quite. I almost have a 2 and almost have a 3, but not quite. Okay, so how can I factor this? Well, I could use AC grouping. A times C is 4 times 6. So I'm looking for an m and an n, so that m times n equals 4 times 6 or 24, and m plus n equals negative 9. Well, I see that to have m times n be 24, to be positive 24, I need to have the same sign. To have m plus n be negative 9, they need to both be negative. And what are my choices for m and n? I could have 1 times 24. I'll fix the signs later. 2 times 12, 3 times 8, 4 times 6, and these would all be negative. What is m plus n in each case? Negative 25, that's not negative 9, negative 14, negative 11, and negative 10. So this does not factor over the integers. So it turns into 4x squared minus 9x plus 6. That numerator doesn't factor into the integers, so it's not going to have a factor of x plus 6 or x minus 3, x plus 2. So that is the best we can do. Okay, so let's look at 2 exercises. We'll take about 8 minutes to do these. And same thing for these ones. Don't get don't get thrown off by the simplicity of the denominators of the first one. Those are basically just prime numbers, right? They're the equivalent of prime numbers. Like x plus 1 is like its own little prime component, and x minus 3 is its own little prime component. Is that? I had a copying error here. This is exactly the same one that we did above. I don't think this one we did, right? Yeah, that doesn't look from. I copied something over incorrectly. Let's just change this one on the fly. Let's make it a minus. All right. So hopefully that doesn't turn out too bad. So I must have copied the same problem twice when I was copying my notes over. But okay, so take a look at this one. Again, it still has these denominators that are like prime components, but this one down here, the denominators are going to require a little bit of work to factor to get them into their, kind of building block form. So take about 8 minutes, look at these two exercises, work through them, and as usual, in a minute or two, I'll kind of start working through it. If you get stuck anywhere, you can take a look back at the screen. Okay, it's about 7 minutes, so let's look at these two. So looking at this first one, again, the denominators are already like prime factors. X minus 4 is just x minus 4. That's its own building block. Same with x plus 7. So the LCD just ends up being the product of the two, x minus 4 times x plus 7. For my first fraction, 2 over x minus 4, I need to multiply the denominator by x plus 7 to make the LCD. And I need to multiply the numerator by the same thing so I don't change the value. And similarly for the second fraction, 7 over x plus 7, need to multiply the denominator by x minus 4 and the numerator as well. I can write these over the common denominator and then combine them together to make 2 times parentheses x plus 7 minus 7 times parentheses x minus 4, all divided by x plus 7 times x minus 4. And now I want to simplify. I want to see if there are any common factors I can divide out. So my numerator, I multiply it out. 2 times x plus 7 is 2x plus 14. Minus 7 times x minus 4 is minus 7x. And then minus 7 times minus 4 is plus 28 over that same denominator. Now I combine like terms. 2x minus 7x is negative 5x. 14 plus 28 is 42. So I get negative 5x plus 42 over x plus 7 times x minus 4. That numerator has no common factors that can be factored out. There's no further simplification that can be done. So this is the simplest form. Okay. For our second one down here, 2x over 3x minus 3 plus 5x over x squared plus 3x minus 4. Both of these denominators can be factored. So we start with 3x minus 3. This can be factored as 3 times x minus 1. And be a little careful when doing this factoring. I had a typo in my writing there for a couple of seconds, then fixed it. But 3 times x minus 1. And then x squared plus 3x minus 4, we see that that can be factored as x minus 1 times x plus 4. Looking for two numbers that multiply to negative 4 that add to positive 3. That's plus 4 and minus 1. So I see this kind of shared building block of x minus 1. I only need one of those, and I'd be able to build either the 3x minus 3 or disassemble that and build the x squared plus 3x minus 4. So my LCD is 3 times x minus 1 times x plus 4. For my first fraction, 2x over, well, 3x minus 3, our truth to write that is 3 times x minus 1. I see I've got this bit taken care of, but I need an x plus 4. So I multiply by x plus 4 in the denominator, and then so I don't change the value of the thing, I multiply by x plus 4 in the numerator as well. For my second fraction, I have 5x over, well, I could write it as x squared plus 3x minus 4, but it's a little more helpful to write it as x minus 1 times x plus 4. What I have here, I've got these bits taken care of, but I need to stick a building block of 3 on there in the denominator, and then of course in the numerator as well, so I don't change the value. And then what do I end up with? Well, kind of multiplying and then adding, I end up with 2x times parentheses x plus 4 plus 5x times 3 all over this lowest common denominator of 3 times x minus 1 times x plus 4. Now, again, I've gotten all of my operations taken care of, my overall operations, but now I want to, so I've got this all under one rational expression, but I want to simplify this rational expression. So my numerator, I'm going to distribute out. I get 2x times x, 2x squared, plus 8x, and then plus 15x. I'll combine like terms, the 8x and the 15x can combine together to make this 23x, but 2x squared plus 23x, I suppose I could factor a factor of x out of there, but I can pretty easily see that's not going to divide out with anything. And there's nothing else that can really factor out of here. So no real simplification to be done. This is the final answer. Any questions on either of those two? Okay, let's take a look at this example. So let's look at simplifying 6x over x squared minus 25 minus 3 over x plus 5. So once again, I'm going to take my denominators, move them over here, and get a factorization. Well, x plus 5 is prime. It's like its own building block. There's nothing we can really do with that. X squared minus 25, well, we might recognize that as a difference of two squares. X squared minus 5 squared, that means that factors to x plus 5 times x minus 5. And my LCD then is just x plus 5 times x minus 5. And I come over here again and I write 6x over, and maybe I'll choose to write the x squared minus 25 in its factored form. And then I ask, what do I need to multiply this denominator by, x plus 5 times x minus 5, to make the LCD? Well, actually, basically just 1, right? In fact, I actually don't really need to change this first fraction at all. I can just leave it as it is. It already has its denominator being in the LCD. So we can just leave it as is. And then minus 3 over x plus 5. What do I need to multiply x plus 5 to make the LCD? I need to multiply by an x minus 5. And if I do that on the denominator, I better do that in the numerator as well. So I have my denominator, x plus 5 times x minus 5. And then I have 6x minus 3 times x minus 5. Clean up that fraction line a little bit. We don't need all that extra over there. Okay, so at this point, I've combined everything down into a single rational expression. And my goal now is to simplify. So I don't see anything right away that would divide out, but I'll distribute, combine like terms, see if anything can be simplified further. So I have 6x minus 3x, and then plus 15. Over my denominator. Or that's 3x plus 15 over my denominator. I see that that's 3 times x plus 5 over my denominator. So I actually do see that I'm going to have some cancellation. My x plus 5s can divide out, leaving me with simply 3 over x minus 5. And I might want to be a little bit careful here to append x cannot be plus or minus 5. Because we divided out the x plus 5, maybe it's good to make note of that those are restricted values explicitly over here. So we did get a little bit of simplification at the end for this one. Things worked out right, and we were able to divide out that x plus 5, making things a little bit simpler for our final answer. Okay, let's look at these two exercises. Maybe let's take about 9 minutes to do these two exercises, and we'll come back and discuss them. I don't think we'll get to the last little subsection here, but I think it'll be good to revisit this again on Thursday, wrap up the last one example, two exercises, and then move on to the very last topic. So we'll knock out these two exercises in about 9 minutes or so. So take your time going through this. You know, there's a bit of factoring to do here. So so go through it carefully. It's also a nice little factoring review, and we'll come back in maybe 8 or 9 minutes and discuss. Okay, it's about 9 minutes, so let's take a look at these. So our first problem, we start off by factoring our denominators. X squared plus 7x plus 6 factors into x plus 6 times x plus 1. And x squared plus 4x plus 3 factors into x plus 1 times x plus 3. So we can kind of share this x plus 1. And our LCD is x plus 6 times x plus 1 times x plus 3. So our first fraction, we get 3x over, and then we'll choose to write the x squared plus 7x plus 6 as x plus 6 times x plus 1. We have two of our building blocks taken care of. We need to multiply by x plus 3 then. So we multiply by that on the bottom to make the LCD, and then of course on the top as well, so we don't change the value. For our second fraction, 9 over x squared plus 4x plus 3, we'll choose to write that as 9 over x plus 1 times x plus 3. And again, we see we have two of our building blocks accounted for, but we do need to multiply by the x plus 6 on the bottom, and then on the top as well. We can combine these together now that we have an LCD. We have everything over our common denominator. So our denominator is x plus 6 times x plus 1 times x plus 3, and our numerator is going to be 3x times x plus 3 plus 9 times x plus 6. And be careful when multiplying this out. Somebody caught that I had made an arithmetic error, so good eye there. Thank you for letting me know, and I came back and fixed it. So we have 3x squared plus 3x times 3 is plus 9x, and then plus 9x, and plus 9 times 6 is 54. So I originally had 6 here, but it should be 54, so good eye on that one. Or that's 3x squared plus 18x plus 54. We do see there's a factor of 3, and of course, over the same denominator. We do see there's a factor of 3 in the numerator that can come out. So that's 3 times x squared plus 6x, and then 18 times 3 is 54. So we had 9 times 6. If we take away, say, the factor of 3 from the 6, that makes a 9 times 2 times 3. So 9 times 2 is 18. Now our question is, what do we do with this x squared plus 6x plus 18? Can that factor? Maybe that has a factor of, say, x plus 3, and we'll be able to divide out, a factor of x plus 3, something like that. Let's check. X squared plus 6x plus 18, to factor that, I'm looking for two numbers that multiply to 18 and then add to 6. So that's what I did over here in this little bit of scratch work. So I know that they've got to be the same sign to make a positive product, and they have to both be positive to add together and make a positive 6. So I could have 1 times 18, or 2 times 9, or 3 times 6. If I keep going up, 4 and 5 are not factors of 18. And if I get up to 6, I've repeated 6 times 3 is the same as 3 times 6. And none of these, 18 plus 1 is 19, 9 plus 2 is 11, 6 plus 3 is 9. None of them make a sum of 6. So this does not factor into the integers. It's not going to have a factor of x plus 6 or x plus 1 or x plus 3. And this is our final answer. And the next one, simplify 6 over x plus 6 minus 12x over x squared minus 36. Again, we come off to the side over here. We look at our factorizations. This is just the equivalent of getting the prime factorization if we were dealing with numerical fractions. So x plus 6, well, that's just the prime component. This is just x plus 6. That's the building block that I need for that first denominator. My second denominator, x squared minus 36, can factor into x plus 6 times x minus 6. That's a difference of 2 squares. And I see my LCD ends up just being x plus 6 times x minus 6. So I bring down my 6 over x plus 6. What do I need to multiply x plus 6 by to make my LCD? Well, that would be x minus 6. I multiply it on the bottom, and then, of course, on the top as well, so I don't change the value. My second fraction I bring down, 12x over, and I'll choose to write that denominator as x plus 6 times x minus 6. But that's already the LCD. I don't need to multiply by anything to fix that denominator. It's already the lowest common denominator. And I can multiply my first two factors together, 6 times x minus 6, and then subtract 12x, all in the numerator divided by that common denominator. And what could I do here? I suppose I could multiply out, combine, factor. I might notice that this factor of 6 shares a factor with the 12, so I could write this as 6 times x minus 6 minus, well, 12 would be 6 times 2 and then times x. Or this would be 6 times x minus 2x is negative x minus 6. Or really, this is negative 6 times x plus 6. I see the x plus 6's can divide out now. And I get negative 6 over, and I guess I don't need the parentheses anymore, x minus 6. That's a divided by line there. And since I divided some stuff out, I probably want to explicitly state my restrictive values that x cannot be plus or minus 6. That x cannot be plus 6 is still kind of implicit in this expression, but we lost the restriction, we lost the evidence of the restriction that x cannot be negative 6, so let's explicitly write that. Okay, so again, next time we will go through one last example, a couple of final exercises, and then we'll talk about the last fairly small compact section on complex rational expressions. So when we have rational expression divided by rational expression, how do we deal with that? So we talked about multiplying, adding, subtracting rational expressions, and now dividing rational expressions. And that will wrap up our material for chapter 8 for rational expressions and the material for the course. And then, of course, the final exam coming up shortly thereafter. All right, that is all that I have for you today. Let me stop the recording.